Our plenary speaker for today is Professor Shlomo Shammai from the Technion Israel Institute of Technology. You know, Israel is a small country, but with many information theorists. Some would say too many. And Shlomo is one of the most prominent among them. Certainly he is the most prominent in the area of transmission over noisy channels. And in particular, he's known and famous in the area of broadcast channels, where he is considered as a world expert and a role model for many of us. Let me tell you briefly his academic career. Shlomo Shammai received, he's actually a student of the institute where he is now teaching. He received all his 3 degrees, Bachelor of Science, Master of Science, and PhD in electrical engineering from the Technion in the years 75, 81, and 86, respectively. During the years 75 and 85, he was the communication research labs in the capacity of a senior research engineer. And since 86, he's with the Department of EE at the Technion, where he is now William Fondler Professor of Telecommunications. His research interests encompass a wide spectrum of topics in information theory and statistical communications. Shlomo Shammai is an IEEE Fellow. He is the recipient of the 99 Van der Pol Medal of Ursi and the co-recipient of the 2000 Donald Fink Prize Paper Award, the 2003 and 2004 Joint IT Communication Society's Paper Award. He's also the recipient of the 85 Alon Grant for Distinguished Youngest Scientist and the 2000 Technion Henry Tau Prize for Excellence in Research. He has served as Associate Editor in the Shannon Theory of the IEEE Information Theory Transactions, and also has served in the past and in the present, again now on the Board of Governors of the Information Theory Society. Now Shlomo asked me to tell you just this very brief biography of his, and I respect his request, although I could tell a lot about how he influenced my academic career, the academic career of many young scientists and old scientists here in the audience. Let me just give you a friendly advice. Please hear very carefully what Shlomo is going to tell you today, because I heard from Andrea that on Friday there is going to be an examination on this material, surprise test, and the Board of Governors didn't decide yet what he's going to do with those who failed the exam. So let me invite
Oh my God!
Questions? You have many questions. Let me invite Shlomo Shammai to tell us about reflections on the Gaussian broadcast channel, progress and challenges.
Thank you, Rami. Thank you for the kind introduction. I'd like to thank the organizers and the TPC chair for the invitation. I'm really honored. Let me start with the disclaimer. I will not, and practically cannot provide a comprehensive overview of all the problems, results, ideas, concepts that are associated with broadcast channels. Rather, I'll focus on simple models, namely variants of the Gaussian broadcast channels. And for these, I shall try to overview classical and recent concepts and some of the more recent developments. The simpler the model is, the more details it will be described with. And I must say, this kind of a presentation is really reflects personal taste and inclinations, and this talk is no exception. So let us start. One thing I don't have to do is to motivate this talk. Because now broadcast channels are really a central component in communication, either wireline or more pronouncedly wireless. And they're all over. And speaking about broadcast channels, the central result that opened the whole field by Tom Cover, the paper that introduced the problem and actually matured it quite a lot in that single paper, deals with the basic configuration of the broadcast channel, where we have a transmitter which is to transmit messages reliably to, say, 2 or more separate destinations, receivers, where each receiver is to decode a common message and its own private message, here Z and Y, and we'll stick to simple models. X, the channel input, is subjected, yes or no, to certain constraints. Y and Z are the outputs. This is the regular characterization of information, the characterization of the transition measure. And that's the problem. What is really surprising is that we are still unable to solve it in full. That is, to provide the capacity region of such a simple multi-terminal setting. And this resists the best attacks for decades. Yet, many of very interesting and important special cases are solved in full. And I really will mention maybe some later on. The most important one, and the one that we will discuss, is the degraded channel, and other cases which are fully known. Focusing on the degraded channel. What is a degraded channel? A degraded channel, just by the figure, is such a setting where the component, the less favorable observed signal, Z, can be viewed as a transformation of the better signal Y through some channel. This channel could be actually the same as the one resulting from the decomposition of the probability distribution, and then it's physically degraded, or another one. Doesn't matter, because the broadcast capacity region that we know very well depends only on the marginals. And the main reason is that the receivers do not cooperate. They decode their messages separately. As promised, let's go to the simple example. But first, what is so important about this degraded channel? As we said, we know to information theoretically characterize in full the capacity region, and it's written here. And as typical in this kind of problem, it has to do with an auxiliary random variable, traditionally here designated by U. And this is the two-user capacity region. R common is the common rate, RZ, the private rate to the degraded, or the receiving point, degraded destination, RY, the rate for the better destination, and the probability space decomposes in a Markov way. Given X, U is independent of the outputs. And this very important result is due to Bergmans and Gallagher. So let's take a very simple example. The Gaussian thing. Here is the Gaussian channel. X input, Y. And the outputs, as said, Y is the better output, therefore the noise, the variance of the noise of Z is larger than that of Y. And this is a degraded setting in general. Why? We already said that everything depends only on the marginals. If it depends on the marginals because of the divisibility of the Gaussian random variables, the noise at point Z could be written as a sum of two Gaussian random variables, and that's it. This is the extra, the additional channel. So what about this? The capacity region of this channel is known in full and written here. And the parameter alpha, which ranges from 0 to 1, gives the whole curve of the capacity region for certain parameters. And it beats also the TDMA straight line, which is the very basic thing that one could think of doing in the broadcast setting. How is it achieved? Let's see the achievability part, which is very simple and represents the achievability on a degraded channel in general. It is done by superposition coding. Here in the Gaussian regime, it's really elementary. You just break the transmission signal into two, xz plus xy. Xz is to carry the common message and the private message to receiver z. That can be decomposed again. xy to carry the private message to receiver y. xz, this is the power associated with xz, independent, this is the power associated with xy together, its p, the average power constraint. Now, receiver z sees the signal to the beta receiver as noise, and then from the regular single user Shannon formula, we can see that the rate, we speak just about the achievability, is that its power and its equivalent noise. The beta receiver, what it does, the beta receiver definitely can do whatever the worst one does. So it decodes the signal Z, removes it, cancels it out, stays only with its own noise sigma y squared, and with the power of its own, the signal directed to him, alpha p. So this is the rate. So no wonder that this is an achievable rate. And superposition is key with interference cancellation. Let's see another way to achieve these points, which will come handy later on. Dirty paper coding. What is dirty paper coding? A single user problem. A message is transmitted to a destination. We have the regular Gaussian channel, plus another noise, say Gaussian, which is known in advance, beforehand, to the transmitter, the transmitter is power constrained. This problem falls under the general setting of Gelfand-Pinsker, transmission on channels with in-memory channels with state information, with state known to the receiver. We know the information theoretic capacity characterization, and for this specific problem, Costa chose the parameters in such a way and came up with a very surprising conclusion that one can achieve the Gaussian capacity like S, the interference S known to the transmitter only was not there. It doesn't cost power to eliminate its interference at all. And that has been extended to vectors, and there are also many papers that deal practically how do we construct codes that come very close to those theoretical results based on LDPC and different ideas. So how do we use this? In the very same way, again, decompose the signal into two. xz carries the common message and the private message to receiver, z with that power. But xy now looks at xz as the interference known to the transmitter. Of course, the transmitter produces it himself. And the paper codes against xz, taking in account that the noise is of various sigma y. You remember the alpha there depends also on the noise. So the rate to the y receiver, just by dirty paper, is this. No harm is taken from it. The rate to the z receiver is whatever happened, because xz and xy, it so happens that they're independent in the Costa setting. So with Costa, again, we can have the same, and of course, the common rate can be decoded at the beta receiver. It can do anything that the worst receiver can do. Okay, fine. That's all achievability and very simple. How about the converse? Converse relies on the entropy power inequality, written here in a conditional in a conditional form, that is, if x and y are conditionally independent on conditional on u are independent, we have the classical entropy power inequality given here for vectors. We'll need that. And it is an equality for vectors when both are conditionally Gaussian independent, but with proportional covariance matrices. And for the scalar case, scalars are always proportional. So this is the key to the converse shown by Bergmans, and here I borrow from El Gabal's course notes, very simple presentation, but without the Fanon, we don't need the Fanon once we have the capacity region of the degraded broadcast channel. The central element is just that we can write Z as the output associated with the worst receiver as Y plus additional noise, and apply the entropy power inequality here. And I won't go really through the most elementary details, but that's all. One comment is EPI is central here. It's really instrumental. One of the most classical applications of the EPI, of the entropy power inequality. Okay, so let's do the converse without the EPI. And let's look at another interesting result by Gaussian and Verdoux, the connection between mutual information and mean square error. Here we have a single user Gaussian channel with input x scaled by SNR. X is any input. We have this relation. The derivative of the mutual information with respect to SNR is just related with equality to the minimum mean square error for any input x. And there are many generalizations that we won't be needing here. For a Gaussian input, no big deal. We know the optimal estimator, which is linear, the minimum mean square error, the mutual information. You see the derivative relation immediately. For, say, binary symmetric input, it's more difficult to see, but can be verified. Here is the C. Here is the mutual information, and easier to see it on a plot. Here is the Gaussian minimum mean square error, which of course upper bounds any minimum mean square error of any variable of the same variance. The integral of the Gaussian mutual information, the Gaussian mutual information, the binary minimum square error, the binary related mutual information, and a property that we will need is the unique crossing point property. Saying what? We said already that the Gaussian MMSE upper bounds any MMSE of another variable on the Gaussian noise with the same variance. Okay, let's scale down the Gaussian MMSE. We scale it down the power by rho. So it starts at 0 SNR, it's only the variance, the MMSE. It starts low, so it's negative at SNR 0. At some point, it crosses. It can be shown that it crosses, because asymptotically for high SNR, it doesn't depend on that rho, as long as it's not 0. And the idea is that it crosses just once. Once it crossed, the Gaussian will always be the winner. No two crossings. And that's formally said here. We really don't need it. And the whole thing can be generalized also to conditional variables. And let's see what we mean just on the figure much easier. Here is the binary thing. The Gaussian, now I scale down by the factor of 0.8. Here it crosses. Once it crossed the MMSE, that's it. No other crossing. It will stay above. This has value of its own. Look, we can upper bound the MMSE by a Gaussian, but with a reduced power from some point and on. And actually has many other applications, this property. And We can indeed also extend it to cases where this Ux is a condition distribution dependent on U, and we are interested in the total expected minimum mean square error. Just to mention how one proves this, the proof is not too difficult and is based on higher order derivatives of the mutual information. This is second order derivative of the mutual information, and some use of Jensen inequality. Okay, let's go back to the broadcast channel. And let's go back to the broadcast channel. And here we scale it even, maybe the natural scaling to start with. SNRZ, SNRY, and SNRY is larger than SNRZ, the better channel. N is of the same variance. Okay, we said we know the capacity region, one of the few examples that's known in full. Here, Ry is smaller than this, Rz is smaller than this. This is a mutual information decomposition. And because of the Markovity, that is, given X, U and Z are independent, we have this. And we contrast not entropies, mutual information, this against this, which is more natural to deal with. Of course, the IXZ is no larger than that, which is achieved by Gaussian. So, MMSE is very handy. Here we write the mutual information IXZ given U in terms of IMMSE. But what is IXY, the better receiver given U? It's the same expression, only the integral is over a larger range. SNRY is larger than SNRZ. That is, we can write it in this form. It's the worst thing plus the integral over the difference. Fine. We immediately can write there is an alpha where IXZ given U equals to that. Why? This is non-negative. It cannot be bit 1 plus log 1 plus SNRZ, of course. So there is an alpha, some alpha. And here we have this equality. This equals to this. So what does it say? On the figure, on an SNRZ, we found an alpha that the Gaussian expression with power reduced by alpha equals to what is known for the random variable x, which here is taken to be binary. But we know that the MMSE of that variable starts higher because the Gaussian has been shrunk by power. And if the areas are the same, somewhere it beats it. The Gaussian somewhere crosses. But if it crossed, that's it. So the crossing point happens before SNRZ. If the crossing point happens before SNRZ, we know that at the region SNRZ and SNRY, the Gaussian is already the winner. So, this integral, which differs between the two expressions, is upper bounded by this. And that is it. Why? Okay, the first thing, IXZ upper bounded by that, this equals to that, gives this. IXYU, we said this, it's IXZ giving you, and that integral which is upper bounded by that is this. Okay, and that's it. One could say, look, what's the big deal? We know already that MMSE and differential entropies are connected. You yourself said that. Here is the formula. Moreover, the EPI was very elegantly proved by Verdoux and Gould using the psi-MMSE. Even more, the IMMSE relation and EPI are intimately related to the De Bruyne identity. But no. Here we didn't use the IMMSE methodology to show EPI and then use the API de Bergon's way. It is very different on first principles with very different properties. And this result is presented here for this first time. I was warned not to do that, but couldn't resist the temptation. Okay, so let's go to some challenges. Fading. Scalar, still scalar broadcast. Say we have fading, known to the receiver. Let's make the problems very simple. What do I mean very simple? Let's the fading of the two channels have the same statistics. Having the same statistics says what? That we do have a degraded channel because the Z noise is larger. So at least we find information theoretically wise. So what's the problem? Say we stick to Gaussian Colboots. Immediately one can identify the achievable ranges in the ergodic setting, no big deal. We know also the information theoretic characterizations and the graded channels. I look at just at this special case. So what's the problem? How do we show that U and X are jointly Gaussian as conjectured very recently? Our API comes to help, no? Not exactly. We pay a Jensen penalty and not to the right direction. Does it work? What do we know? We can show the 0-1 fading case, either by IMSC or by EPI. We can show the more any finite state fading with the uniform degradation, meaning the best fading of the worst user is still worse than the worst fading of the best user. That we can do. In general, this problem is still open. Let's go to another setting. Still, Gaussian channel, Gaussian broadcast channel, multi-antenna. Multi-element transmitter receivers with single or many antennas. And say no common rate. And we have a total average power constraint. TDMA, this TDMA, no big deal. No chance of being good, even in the scalar case it was beaten. How about beamforming? Let's just beam to both users and optimize the beam. Yeah, there is a game, very beautiful game. And moreover, if we look on the behavior, how does it behave with SNR? The slope of beamforming, optimized beamforming is better twice, meaning that we do retain all the degrees of freedom, which is very nice. Still, not always we are interested in that. If we do dirty paper, that dirty paper coding gain even more. But here, dirty paper coding is a must, is not an alternative to superposition coding. Because what is better, what is worse in this matrix formulation where ordering is quite problematic in general. So, just a short historical perspective. The problem is not easy because this Gaussian broadcast multi-element vector MIMO broadcast channel is not a degraded problem. Not easy. The first work examined two users by Kaira and Shamai. This is my friend, long-time collaborator. And the DPC, as well as an upper bound, the Sato upper bound, were central there to show that, to settle the problem for the sampling. It was extended, the view was significantly extended by Tsevis Vanadu, Vishwanaj, and Alan Goldsmith to more than two users or many antennas, introducing the concept, the important, very important concept of multiple access and broadcast duality. Then another results historically came and showed that if we stick to Gaussian signaling, DPC is the best that one can do. Again, derived by two groups. And the problem was settled completely by Weiger-10, Steinberg, Shamai, who found the capacity region. And this capacity region now can also be, for the two-user case, derived based on also on entropy extremable entropy inequalities. So just to say a word about duality, which is very important. Duality, the multiple access dual channel, where the users transmit to the multiple antenna receiver, just the opposite, is very convenient. Why is it so convenient? Because there we know everything. We know the capacity region of the channel, no big problem. But it's theoretical. We know the geometrical property, the polymetric structure of this problem. That is the Wiener cover pentagon in higher dimensions. And the way to achieve those vertex points via detection and interference cancellation, as we see, given with permutation of order that will give all vertex points. So that is very simple, similar to the dirty paper coding approach on the broadcast channel. Indeed, we have an ordering. The first user takes the interference of all others, the signals of the first user. The second dirty paper code against the first, the third against the first two, and so on. And who is the first, who is the second, who is the third? That's subjected to any permutation. So, and indeed, so it so happens, and that's the duality concept, that the dirty paper region of the broadcast channel is no more than the union of all pentagons, as we see here. And that's important because the broadcast channel, the multiple access channel, we can deal with, solve, and then reflect the results to the broadcast channel, and even do it for more interesting constraints like per antenna and any linear constraint, but a stronger concept of the U-LAN duality. Okay, that's fine, but wow, how do we show that this is the capacity region? That's all. Entropy power inequality, our strongest tool, fails as is. Why? Because for vector we need the covariances of x and y, or the conditional u, x, y to be proportional. That doesn't happen. So let's see what was the central idea, and present it in what is known the aligned MIMO broadcast channel. That is, the H matrix is unit matrix, but the noises have different covariances. Still, it is not degraded in any sense. This is done via the concept of an enhanced channel. What is an enhanced channel? An enhanced channel is a channel where designated by these primes, where the noise uniform of nk prime is better in this sense than the original noise. That is, this channel is uniformly less noisy, therefore its capacity region is an upper bound. Fine. So the proof is based on this concept. Say we have the dirty paper region, and we have an external point which is not included in the region. The first step is to show that there exists an enhanced, aligned, degraded MIMO broadcast channel whose DPC region also does not contain this point. And the second step is to show that this DPC region of the enhanced channel is actually the capacity region of the enhanced channel. And there, by miracle, not exactly miracle, we do have the proportionality properties that enable the use of the entropy power inequality. Okay, let's just demonstrate this whole setting, this whole framework for an application, not only just one transmitter. Why not many transmitters? Here we have a cellular system. All antennas are somehow co-processed by a central processor. So what if they're not collocated? And this is a variant of Weiner's model, where each mobile, say, receives the signal from two antennas, characterized mainly the mobiles who are in soft handoff position. So this is a standard MIMO broadcast channel, which can be characterized by the same matrix notation, but the power constraints are per antenna. The total power constraint is nothing. We have done a power amplifier per base station. So we use this concept, the stronger concept of the U-LAN duality, where the more stringent constraints actually are expressed here in the dual space by minimizing over the noise covariances under certain conditions. The exact details are not so important. And that formula for this model can be worked out explicitly to give a very neat result for the cellular model. And there are follow-up works, including in this conference. So what are the challenges? How about fading? This we didn't include fading here. Why fading is a problem? A problem because we have difficulties in characterizing the limiting eigenvalue distribution of finite diagonal random matrices, not full random matrices. That is why this is a problem, and that is why in this work we have only bounds and cannot nail down the result. Planar Wiener model. Here the main difficulties are just more details. In a way, I was not fair. I really was not fair. Why wasn't I fair? Remember, when I went to the MIMO broadcast channel, first thing I did, no common rate. Why? What happens if we do have a common rate here? Just two users, it's complicated enough. And the covariance constraint, which is more general than just a power constraint, accounts for all, per antenna power, total power. What do we know here? Achievable region? We don't know. G-Smith. Achievable region, we just split the signal into three. The covariance QC stands for the signal that transmits the common rate. The common rate takes interference of the signal associated with both private messages, and it should be received at two receivers. Then we have the minimum, the compound relation, the private rate to one of the users. Since the common rate is detected, removed, and forgotten about, takes the interference only of the second user, and the second user, who is one and who is second, is a matter of permutation. The second user, dirty paper codes against the first one, no interference at all, just the noise. And one and second can be switched. So we know this is an achievable region. Is it the capacity region? Actually, we don't know. It's a challenge. The degraded message set, no private message is set in this work mentioned above. Actually, more is set. Apart of outer bounds, we know that per a given common rate, we know how to optimize some rates. And we know that this is indeed the capacity region for the aligned channel if the common rate is not low. It's above some threshold. We don't know that this is the capacity region as we conjecture in general. We spoke a lot about DPC. What can we do without the DPC? Just from practical aspects. Like linear pre-coding. We can do a lot, but on practical things, I just don't say anything, but it is also an information theoretic problem because we are looking for the best achievable strategy for what is known the cover and the Mullen-Hajic-Persley region, which predated Martin region. And we'll come to that when we'll speak on more general models. One last word on that, the extremal inequalities, extremal entropy inequalities here. The maximum of this expression over all measures, where mu is larger than 1 and n are general vector noises with the covariance constraint on X is achieved by Gaussian measures. And that, combined with Markov 5, the outer region, can also be used to show the capacity, the converse of the capacity region of the Meinl-Broadcast channel. The question is, what about IMMSC? It can be used, but this is a challenge that I state here, but my feeling that it can be used to do it very elegantly. Still haven't been able to show it. One central factor here is CSI, chance state information, which implicitly all over assume the transmitter knows all the channels, all the matrices, the channel matrices. It's not always the case, especially not in practice. So what happens if we make the problem more practical? That is, some of the information is known indeed at the transmitter or the receiver. The tilted information, that's the noise in estimation, whatever you like, just known to the receiver. It cannot be conveyed through a finite feedback channel to the transmitter. What are the implications then? Another well-defined broadcast problem, and not an easy one. Say we want much less than the capacity region. Summary, throughput, even not that, just the degrees of freedom, the multiplexing gain. What's the impact of the multiplexing gain? Let's see. It's already in the original paper of Kaira Shammai it was shown. If everything is known, one gets the full multiplexing gain, not even, which so even if it's zero force. In the minor case, where the receiver cooperates, Teletar has shown you don't need even the transmitter to know the actual realization to get the multiplexing gain. Where we have no CSI at the transmitter, Kaira Shammai for their simple model mentioned that everything is lost in terms of the MIMO broadcast channel with multiplexing gain, and Jafar and Goldsmith even came up with scalar bounds on that. And different opportunistic approach, which are, they lose everything in terms of this multiplexing gain. They're very important, but in this term, they lose everything, even not one. And if CSI is known to known, forget about the problem. Even if with full cooperation, there is no logarithmic law. So what the conjecture we have is that indeed the multiplexing gain is lost, even with a minute but fixed unknown power. And whatever we've been able to show that it's not upper bound trivially by 2, but something less than 2, but fail to show that this is indeed 1. Another very interesting variant of this MIMO broadcast channel is either a compound setting or where we have two groups with so many users in each group. J1 users in group 1, J2 users in group 2. And there are two messages. One message is to be decoded by all users in group 1, another by all users in group 2. Compound MIMO broadcast channel. Not an easy cookie. There are results. This problem is not yet solved. Let's settle for less, for much less, the multiplexing gain region. The multiplexing gain region, even that is not solved. We do have upper bounds and lower bounds. And luckily, they meet for the case where the number of users per each group equal to the number of antennas, but not in general. In general, we probably do have a feeling of what happened, and that's a conjecture which we so far resisted our attacks. So, challenges here. Why just the multiplexing carriage? It's a very, very practical problem of partial translate information. What is the full solution of the capacity region? Is it related to what is known writing on fading paper? Is the optimal technique related to that? I don't know. Let us go back for the last minutes of the talk to the original broadcast channel. Going back to the original broadcast channel, it's the same slide that I had, the cover presentation. And let's see some challenges based on a network perspective. What do we know first about that? Achievable region. It's the Markov region with common rate written here, not just like in her paper. This is what we know. Wherever we know the capacity region, it falls under this. And if we choose the probability space, all auxiliaries to be independent, this is what I mentioned, the cover by the Buehler-Hajduk-Persley region, which, in terms of MIMO broadcast, says what can be done without dirty paper, without having U and V correlated. Still not a problem. As far as upper bound goes, the best we know is a recent result by Nair and Gamal. Here is Martin 5, actually, in a paragraph that follows that theorem in her paper. Probably she meant more than just this, but what's written there in just this. So, network perspective, feedback. What does feedback do in the broadcast channel? We don't know quite a few results. For example, for a physically degraded thing, forget about it. Rate-wise, forget about that. Won't help. Stochastically degraded, that were the same without feedback. They're not the same anymore. Helps, even if we have one branch of feedback. How about a more general look, a generalized feedback channel? A generalized feedback broadcast channel can account for everything. The Shannon feedback that we see. Actually, receiver cooperation, which is done from here. And relay. A relay channel can be put also like that here. This one through the channel, which is a general, can help the other one. And we have lots of results on that. Mostly recent. In cooperation, different setting, orthogonal cooperation, Tabora Serveto, more general cooperation, Liang Veravali, and relaying with the summarizing authoritative tutorial to appear in FAT by Kramer, Marik, and Yates on this cooperation business. Secrecy on the broadcast channel. Very well. Every user should decode its own private message and the common message, but maybe it's better not gain any information, not gain all the information about the second message, where the measure of equivocation is how much it could know about the other message. A very interesting problem with classical Chisholm results and more recent developments. The broadcast channel actually gives rise to communication even on single user channels. It does have nothing to do with broadcast. That is what's known by now the broadcast approach, already motivated in the original cover, paper by cover. Meaning what? There are different states of that receiver. And we interpret them, not knowing that the transmitter, we interpret them as different users with different situations. And that gives a whole set of results which are associated not only with rates. for the fading thing that has been examined by myself quite, and then for the Nino thing, but it's not only associated with the rates. Why? It is a marriage made in heaven between successive refinement and the broadcast approach. The more rate you have, actually the better you can reproduce the source, HDTV or whatever. And about this problem, there are also recent results, including in this conference and in the following workshop in Norway. A general distortion problem may be motivated by the very simple example. Say we have a source, a Gaussian source X, to be transmitted to a number of users. And we have a distortion region, no, wait, a distortion region. Okay, we know already, forget about the separation principle. But for a Gaussian source with the same bandwidth, no bandwidth extension, the best thing to do is just to plug the source as is. Okay, that's not new thing, because we know there are sources that just plugging them in gives you the optimum. Gaspar-Rivoldi, to code or not to code. Okay, but always it used to be an alternative to coding. Here it's not an alternative, it's a must. There is no coding alternative to that. Are we back to analog? And if we are back to analog, then this analog part could serve as side information. So we touch on broadcast channel with side information at the receiver, either analog or another side information. On that, there is really an ocean of literature. And if side information channels, here is this problem, a broadcast setting where we have side information. Surprise, surprise, the network coding that we heard yesterday, butterfly, special case of that. Network coding, classical network coding, just result out of information theory results. There are many results, I don't mention name, and many developments of different settings of partial information to be presented in ITW in Lake Tower. The actual problem, we have queues with rates, and the broadcast transmitter should somehow control the whole thing. Should combine everything together. But how can we do that? We can't. And there are results, interesting results about stability region on top. Let me just come to the conclusions. And the broadcast channel said, it is really a central building block in communication system. And being so, it motivates, the practical application motivates very interesting and very challenging theoretical problems that are not fully addressed, or even not partial. And the other way around, theoretical results are embraced almost immediately in practical systems. An example is linear and nonlinear precoding, especially linear, ideas of linear precoding. But how about the central and basic problem? Should we question the questions as we heard yesterday? The capacity region of the broadcast channel that resists so many attacks. Should we? Maybe it's such some inspirations, a new look that we miss to settle the problem, and maybe not. Maybe our tools are not strong enough. What do we have? What is the strongest tool in our arsenal? Benning. Maybe it's not enough. Neither the manipulations that we do with Fanoinen work. We need more. Maybe it just cannot be characterized in single letter expressions. Maybe. But my personal feeling is not that it can. And we'll see that. And about, my God, it goes back. About literature, really, as I said in my disclaimer, if I stick to that, really couldn't bring much for the interest of time, space, and also personal ignorance. And these are the references. These are the references that are mentioned explicitly in this talk and only, and the single reference or no conference, just the lab. Here, there are hundreds more that I didn't mention, hundreds. And finally, I would like really to thank, my deep gratitude goes to my co-authors, and these are the co-authors on problems that are directly related to this talk in alphabetical order, and I would like to thank you all.
Thank you, Shlomo. It was a very nice talk. And I guess there are some questions, and we have a few minutes for questions. So the audience is invited.
What will you do next, Shlomo?
Have you seen how many challenges? And most of them I just skipped. I just skipped. Have you seen? If I solve one or two, that would be enough. And I invite all of you to do next.